So we can start now.
You can start. It is 12.
Yes.
Okay. So I am in the air.
Yes, sir.
Okay. Hello. Good morning and welcome you all in the 24th talk of MOES Earth Science Popular Lectures webinar series. This is a part of initiative started by MOES to convey the common public, scientists, students from various backgrounds about the activities of MOES. So far, lectures have been delivered on various topics ranging from ocean technology, ocean observations, polar observations, clouds, science of precipitation, cyclones, monsoons, climate change and climate modeling to air pollution. And these talks were delivered by eminent scientists uh, in respective field in a simple way to make understand complex subject complexity of the subject. I would like to thank Honorable Secretary MOES Dr. M. Rajivan and Professor Ravinandan Jaya, Director IITM, for giving me this opportunity, and Dr. Vinu Vatsala and Dr. Gopal Iyengar to make it possible. I would also like to thank computer staff of IITM who have made this thing technically possible in these difficult situations. Before starting the talk, I only say that so far the talks were given by the experts of that subject, but I'm not expert what the talk I'm giving now, and so you have to bear with me. So now, Padmakar, you please start. Hello, yeah, Padmakar,
Yes, sir.
yeah, start. It is not visible.
Wait a second.
This is the 24th talk in MOES Earth Science Popular Lecture Series. The topic is floods and droughts, basic science and predictions. So floods and droughts are recurrent phenomena in our country. With different climatic zones and rainfall patterns in different regions, it has been the experience that while some parts are suffering devastating floods, another part is suffering drought at the same time. So the coexistence of these entities poses a potent threat and presents a major challenge from a science. So the outline of my talk will be the disasters, floods, types, causes and forecasting, and droughts, types, causes and forecasting, and MOES initiatives. So, floods and droughts are hydrometeorological hazards, and disaster risks are increasing. And this is due to the increasing intensity and frequency of these hazards and increasing value of exposed elements due to development and demographic expansions. So these are causing the increase in this. And if you see, this is the all type of natural disasters, and flood and drought are also part of this. So you see, it is last 120 years data, and in recent years, you see how the floods frequency is increasing number, and also the droughts and temperature wildlife things are also increasing. Along with this, the economic impact is also increasing to mitigate these events, natural hazards. And if you see flood and drought, that is also increasing in recent years. So now it is almost more than $250 billion per year is spent for mitigation and this flood and droughts. So, but the good thing is the deaths are decreasing. So here is the decadal deaths due to various uh, disasters. And if you see in alternate decades, so suppose this is 20s, so drought are the most important and killing hazards. But after that, this is flood. So next decade flood, then again drought, again flood, drought. So alternatively, these are happening, but all total is decreasing. And if you see in the recent 30-40 years, this the deaths due to droughts and floods is minimized. And this is due to the good forecasting. And here is the contribution of National Met agencies and also WMO and CWC and in India and this disaster management authorities or disaster managers. So the deaths are decreasing. This is very good. And if you see in India, all type of disasters are there. So landslide, cyclone, due to its typical geography, it is surrounded by oceans and then Himalaya and then monsoon seasons. So all these heavy rainfall, flash floods, thunderstorms, heat waves, cold waves, these heat wave, cold waves are affecting the almost same region. And then flood, earthquake, forest. So almost 68% of net zone area, that is 116 districts, is drought prone, and 40 million hectare flooding is also. So some regions are flood prone, but some new regions also happen every year. And if you have to understand the climatic system, then we have to know that the climatic system is made of lithosphere, atmosphere, biosphere, hydrosphere, and they all are interacting with each other. But new in recent times, there is a new addition, that is anthrosphere. And this anthrosphere is interacting with each of these components. So this is the human induced activities and other things. So here is the so in all spheres of climate systems, human activity increasing, and one of the thing precipitation is the most important factor in occurrence of floods. But many other contributing factors like natural factors, catchment characteristics, soil type, land use cover, anthropogenic activity, river, floodplain, and they also contribute to the flood frequency. Here is just an example of the effect of deforestation.
So rainfall received in both this scenario is same, but one scenario is full of forest, another scenario is very few forest cover. And then you see that runoff is increased when there is less forest cover, and runoff is decreased in the when there is more forest cover. So the more water is available, and this stored water help us to beat the drought. And so the forest and wetlands benefit humans by slowing down water runoff that can cause flooding, and also the stored water will beat the drought. So therefore, if there is any change from here to here, the frequency of drought and flood will be increasing, happening. So the frequency and spatial extent of flood in recent years, if you see, is increasing. And also the if you see droughts in the last 120 years, the first 60 years, and now the current 60 years, and you see that the mean of aerial extent has significantly increased. This is a 4-month SFI. So droughts and floods both have significantly increased. And the projected change, this is the suppose in old climate, and this is the new climate. So old climate, this is the extreme here. So there will be some cold weather and there will be some hot weather. But the new climate mean and variance is changing. So cold will be less area under this cold, but the much more hot weather will be there, and more record hot weather will be also there, which is not there in the previous climate. And similarly, this is the previous climate where light rainfalls are more and moderate and heavy rainfalls are less. But uh, this in the projected climate change, the light rainfall is reducing and moderate and heavy rainfall is increasing. So this is we have shown in a paper that light rain intensity, this is the future changes with respect to 1951 to 1999, and changes in the end of century 50 years, 51 to 2099. So here you will see that the frequency of daily rain rate of light or low rainfall is in the negative, percentage change is negative, and moderate is slightly negative and positive, but heavy rainfall is almost increasing almost all parts of the country and with a good percentage. So, and here if you see, there are 4 models, and this is a multimodal mean. So a strong monsoon means flood, and weak monsoon drought type of situation is both are increasing in the future climate. Also the extent, this is the current GPCP extent of active composite, and this is the break composite. And we see that this is the difference. So the extent and intensity of active and also of break both are increasing in the projected changes. So with this background, I will now first floods types and forecasting. So flooding in India is a serious problem, and every year causes loss of life and damage to buildings, other structures, and animals, bridges, sewerage systems, roadways, canals, and whatnot. And according to recent reports, extreme weather killed more than 1,500 people in India in 2019. And this year itself, more than 200 people have been killed, with heavy rains and floods alone claiming 850. So in 220 already many people, animals are killed, and several million people became homeless. So this is the five biggest floods in 2019. This is in Bihar, this is in Karnataka, this is in Odisha, Maharashtra, Kerala. And if you see this year already within 2 months, this is in Assam, and then Bihar, then Uttarakhand, then Mumbai and Delhi, the city also was flooded. So floods in four states lead to economic loss of rupees 19,000 crore in 2019. And if you see loss due to Chennai flood in 2015, it was almost to 20,000 crores. So uh, we have to study and see what type of floods are there and how it can be forecasted. So if you see types of floods, then uh, fluvial. So fluvial is basically river floods and rainfall over an extended period and over extended area can cause major rivers to overflow their banks, and the water can cover large areas. And pluvial is surface water, so the puddles and ponds develop on the land. Canals are filled to brim and spill over, and gradually a layer of water covers the land. It is like urban flooding, but not sewage system, and it is more in the rural area. And flash floods is in the areas of steep slopes. Heavy rain can cause a riverbed that held very little or no water at first to suddenly bring in fast flowing water. So flash flood is very direct response to rainfall with a very high intensity. And urban floods uh, is specific in the fact that it cause is a lack of drainage in the urban areas, and then if there is a heavy rainfall, then urban floods will happen. And there is another coastal storm surge due to cyclones and extreme weather, high tides, and other things. And groundwater flood is also there when this is supposed to flush. And groundwater flooding um, takes time. And as rain falls over an extended period, the ground becomes saturated with water, and until it cannot absorb any more. And when this happens, water rises above the ground surface and causes flooding. So this type of flooding can last for weeks or sometimes even for months. Uh, flood causes floods cause uh, these are the causes for floods. So excessive rainfall, cloudburst, rapid melting of snow and ice, deforestation, impermeable bedrock, encroachment over the river floodplain, malfunctioning damages of dams, low-lying coastal areas, cyclones and tidal actions, and situation of rivers and lakes, and natural and man-made drainage systems. So these all are causing the, and it has wide impact on individual, communities, societies, economic, environmental, everything. And the consequences of flood, both negative and positive, vary greatly depending on the location and extent of flooding. So it has a negative impact on health. So high mortality rate, waterborne diseases, vector-borne diseases, and sometimes loss of health infrastructure, and social also, loss of life, destruction of crops, loss of cattle, loss of property, then environmental pollution of water bodies, loss of habitat, loss of biodiversity, and economical also, so loss of infrastructure, loss of property, damage, and suspension of transport systems, expenses on evacuation. So we have already seen the economic impact on the natural disasters are increasing. So, but it has some good also for groundwater revival, wetlands renewal, natural fish stock recovery, land deposition, because flood brings fresh water, and with this for irrigation and domestic use, increases fishery resources, improves navigation or transport, and kills insect, washes out acid water, and pushes salt water towards the sea, etc. So flood mitigation through uh, forecasting. So flood forecasting is the process of estimating and predicting the magnitude, timing, and duration of floods based on known characteristic of a river basin. And predetermination of floods events helps the implementation of a structural measures for the mitigation of flood damages, regulation, and operation of the multi-purpose reservoirs with a focus on the control of incoming floods and evacuation of the affected population. So, Central Water Commission is the only agency which undertakes flood forecasting in India, and CWC categorizes floods. This is just warning level. So above this level is above normal. Then so this is green, then yellow, then orange is the danger line, and then red is the extreme highest flood level. So CWC has a dedicated flood forecasting portal, and this every day, any time, if you click on this, you will get this type of map, and then you will get that which area is having above normal flood, which where it is severe flood, extreme flood, and all these things will be there. So flood forecasting is generally attempted by correlation coaxial diagrams, statistical methods, hydrological models, hydraulic models, and data-driven AI/ML models. This is one example that when a number of tributaries affect the water level at the forecasting station, the variation in water level at base station is a location upstream of the forecast station, on the main river, as well as base stations on the tributaries are considered to prepare coaxial diagram. So here you can see this is a flood forecasting for Patna. So it takes account in water level of Bakshar in the Ganga, then Ghagra, it is taking in Dharauli, then Son it is taking Chopan, and on Gandak it is taking Rovaghat. So from all four directions it is considering. So what is 24 hours water level here in Dharauli, in Chopan, in Revaghat, and in other Bakshar, and then they calculate that if how will be this level and how will be it will be affecting on the Patna. So like this, this is the they give the forecast of water level at Patna for hours, and this is just to a station water level at Vatrak and water level at Ahmedabad in Gujarat, and they have plotted and they found that there is a 4-hour lag in Ahmedabad location, and then this is very good correlation. So at least 4 hours in advance, this can give the prediction. So this type of models, which are based on this flow and coaxial diagram, are relatively less complex and provide only peak flow of water level information, and it drops no hint about the shape of likely flood hydrograph at the forecast site. So therefore, uh, uh, we are now using hydrological models, and hydrological models consists of rainfall models, runoff models, which generates the catchment flows and result from rainfall events. And rainfall runoff model consists of a set of equations that, starting from rainfall and evapotranspiration data, allows the estimation of runoff as a function of various parameters used for describing watershed characteristics. And then we use a routing method which predicts the movement of water once runoff reaches the channel system. And routing can be used to determine whether the pulse of rain reaches the city as a surge or a trickle. And this procedure determines the time and magnitude of flow at a point, so hydrograph on a water course from known or assumed hydrograph at one or more points of a stream. So, and then inundation model, which predicts how much area will be inundated. So, real-time flood monitoring and forecast challenges. So, there is lack of data availability in real time, biases in and uncertainty in satellite-based data sets, and also there are biases in various parameters in the hydrological models, and then lack of observed stream flow data, and then there are human interventions. So most of the river basins are highly affected by human interventions. So that also has to be incorporated in the hydrological models. And data availability on initial conditions for the soil moisture and all these things are not very accurate. So reliability of weather forecast is there, but very finer resolution. So here for hydrological models, they need forecast at very finer resolution. So these are the some challenges. And so this is just to show that how GPM is giving the rainfall, how TRMM radar is giving rainfall for Uttarakhand 11 to 17th June 2013, that event, and Chennai heavy rainfall event, and Uttarakhand flood, which 6,000 deaths had been occurred. And now this is the set real-time monitoring and forecasting system, which is implemented at IIT Gandhinagar, and data collection and processing first they do. So data collection of all type meteorological, soil, elevation, sediment, and land use, and then satellite precipitation and CMOP and all those things, and evaluation and correction of this data with respect to this, and weather forecast then from NCMRWF, IITM, IMD, and all these are given to hydrological modeling, that is weak, and also data assimilation has been done, and this gives real-time flood monitoring and also forecast, and then hydrodynamical modeling is run, which gives flood inundation and forest forecast evaluation using satellite. So not only we give the forecast, but then again after given, it is again evaluated by the satellite based inundation. This is just one example on the Ghagra Basin River network. This is Chisapani station, and this is Faizabad station. So this is the stream network of all tributaries. And then the real-time flow simulation is this at Chisapani and Faizabad, and this is from 1st June 2015 to so almost you can say 9 months, and this is just for in this graph only last 30 days. So here you cannot see because this is in thousands, but there is still something. So this type of simulation is being done, how it will be in Chisapani, how it will be in, and forecast is being issued. There is another framework using WRF and probability distribution model framework. This is run at BHU for Kosi River and other Ganga at BHU also. So this is hydrometeorological variables and MSSQL model is run, WRF, and then probability distribution model is giving the runoff and things. So this is the framework of that model. So WRF is run and rainfall has come, and also meteorological variables, and then the probability distribution model gives the runoff and things. And this is just example when they have used this is the hydrographs. So ECMWF rainfall forecast they have used, and this here is ECMWF and ETO. Here is only rain gas plus ECMWF and rain gas plus this. So rain gas is also very much required because once you here there is no rain gas, so simulation will not be that good. So remote sensing is a solution, but again this rain gas will be required. And this is just it is shown that for in India flood visualization and waterlogged area can be achieved by microwave SCATSAT 1 satellite image, and it has the full all-weather capabilities and can detect flooding in the night time also. So you see from July, now it is July 14, 15, 2017, which area is flooded, 19, 20. So this type of flooded, partially submerged and saturated like that, all these graphs can be prepared from. So here we have shown from July. So India's first real-time integrated urban flood forecasting system has been developed for Chennai, and this was developed by a team of 30 scientists from various institutes, national labs, led by IIT Bombay and NCCR of Chennai, and now it is operational at NCCR. So this is and the second system of same type has been implemented in Mumbai this year, inaugurated by Honorable Minister. So these are some efforts which MOES has taken initiative in urban. And the overview of this problem and complexity is this. So there will be rainfall in the upstream, and then upstream flow will be here, and then there is a reservoir. So after reservoir operations, the water will flow, and then in the city, so buildings, road, drainage, fine resolution digital elevation model is available, and there is also directly, so one is through upstream, another is directly through intensified urban rainfall. This city is receiving rainfall, and then there are storm surge and tides are also coming from ocean. So this problem is flooding problem is this in Chennai is very complex, and similar is in Mumbai also. So the framework is first the rainfall and weather parameters, radar data is acquired. Then from NCMRWF, model simulations and quantile regression has been done. Then prediction statistical model for combining multiple ensemble towards quantile rainfall. So these all processing for rainfall, and also radar data is giving nowcasting. So all these are assimilated. And then we also see what are the coastal conditions, tidal and bathymetry, and tidal and surge forecast is also given. So this is also coming to expert flood system. Then coastal condition is also coming. Then hydrology conditions also, water levels, reservoir levels, and hydrological models and forecast. And then terrain conditions, drainage, land use, land cover, topography. So all these things are coming in the expert flood simulation system. And then this will give the inundation forecast from 6 to 72 hours, and also 3D visualization. This is ward by wise maps and tables are there. So first thing is to collect this real-time data. So 10 automatic weather stations are there in Chennai, and 5 automatic rain gauge, 6 radar type automatic water level recorder. And then this is a forecast just to show forecast day based on initial condition of 31st October, the forecast from 1st, 2nd, and 3rd of November. So these are the percentiles. So 80 percentile no flood, 85 percentile no, 90 percentile there is on first, 95 percentile, 99 percentile, and then on second and on third. So this type of figures are and maps being generated. So now I will see droughts, types, causes, and forecasting. So what is drought? So drought is a deficiency in precipitation over an extended period. So first thing is deficiency in precipitation, and usually a month or season or more. And this will result in extensive damage of crops, loss of yield. So this is agricultural drought. And this resulting in a water shortage, causing adverse impacts on vegetation, animals, and people. So that is your hydrological drought. And it will finally lead to fall in employment in agriculture, reduction in purchasing power, issues of drinking water. So this is socio-economic. So this is you see how what are the time duration of different type of so natural climate variability is on the top, and then precipitation deficiency and high temperature, high winds, low relative humidity, greater sunshine, less cloud cover, reduced infiltration, runoff, deep percolation, and groundwater recharge, and also increased evaporation and transpiration. So this will lead to meteorological drought. Then this will lead to soil water deficiency, plant water stress, reduced biomass and yield, and reduced stream flow. So this will generate the agricultural drought. And then the stream flow is reduced, inflow in reservoir is reduced, lakes and ponds reduced, wetlands and wildlife habitat. So this type of result will be a hydrological drought. So meteorological drought is generally starting from 1 to 2 months of water deficiency. Then soil, and this will take 1 to 4 months to respond to give agriculture this, and this will take 4 months or 12 months to respond in the hydrological drought. So So this is the classification of drought. So first is the meteorological drought. It generally start with a lack of precipitation and possibly in combination with high evapotranspiration and resulting from the natural variability of the weather. And it is purely based on rainfall, and it is expressed solely in the basis of degrees of dryness in comparison to the normal or climatologically expected rainfall over a wide area. So meteorological drought is generally measured in the degree of dryness. So then there is agriculture drought. So the soil moisture drought is also agriculture drought is also called as soil moisture drought, and it occurs when the soil moisture is depleted to the extent that the crop yields are reduced and sometimes lead to failure, and crop production goes below the level of sustainable limit over space and time. So this impact on agriculture depends on duration and intensity of flood. And there is a hydrological drought. So both the stream flow drought and the ground flow drought are part of the hydrological drought. And it takes longer for precipitation deficiencies to show up in its components of the hydrological system. And water in hydrological storage systems, reservoirs, rivers is often used to multiple and competing purposes. So flood control, irrigation, recreation, navigation. So all these things. So we will have a hydrological type of hydrological, and then there will be social economic. So this condition arises when supply of some of the goods and services such as energy, food and drinking water, etc., are reduced or threatened by changes in meteorological, agriculture, and hydrological conditions. So, in most instances, the demand for economic goods is increasing in recent years, and also supply is increasing. And when there will be imbalance between demand and supply due to drought, then this socioeconomic will be there. And this is taken from Droughts and Floods by Krishnan, and this report. And you see the interactive mechanism of leading droughts is monsoon droughts, so surface boundary condition, then land surface process, SST, Russian snow cover, INSO IOD. So all these will reflect into the rainfall, and then interactive dynamics of monsoon intraseasonal oscillation and MJO and synoptic scale oscillations. So, and other possible causes are also there for this is solar or anthropogenic and volcanic and stratospheric conditions. So this is beyond our control. So these are the list of major droughts from 2001 to 2015, and this is 30 years period. This is 25 years. So total number per decade is 2. So here it is 2, then it is less, then again 2.7 and almost 2. So in 2000, the recent droughts were in 2000. The northwest and central India was affected, and this was due to enhanced convective activity. And 2002 northwest and parts of India. So July was the most culprit. So the anomalous atmospheric convective activity over northwest and north central Pacific and El Nino was the responsible. So there are various studies. And 2009, most of the country except north and south interior Karnataka. So almost this was the pan-India drought, and various studies have linked various unfavorable phases of two important modes, El Nino and IOD, both equino, and then SST gradient in Bay of Bengal, then prolonged monsoon breaks, and weak cross-equatorial flow and descending motion over the Indian landmass collectively resulted in less moisture supply. And then 2015 also, so I will come to 2015, but the cause was enhanced convective activity associated with the pronounced meridional sea surface temperature and gradient across the central and eastern Pacific Ocean, and that induced large-scale subsidence over the mountain region. So 2015, this is Misra and Bimal Misra's paper, so worst drought in the country. So 4-month SPI, standardized precipitation index, I will come to that. So this is 4-month, so these are the regions, and this is 2015 rainfall anomaly only. And this is the 1 to 4-month dot, and 2015, you see 4-month SPI is very high. And there is already 2014 was dot, 2015 was dot, and then heat waves were more. The heat waves had killed more than 2005 people in 2015. So this combined effects of heat waves, so more hot summer and almost no rain. So this is devastating actually, but it was managed very nicely, and we have not got that much. The forecast was given in advance, and monitoring and all those things were very active. So we have the impact on crop, and this was not that much, but water availability and other things impact was. So there are various indices to measure the meteorological droughts, and one is the percentage of normal. So this is very old. So how much percentage of rainfall is received in this month or this season? But this is very skewed because suppose for there is a station Chitradurga district in Karnataka, and August precipitation of 115 years, mean is 68 millimeter and median is 49 millimeter. So almost 50% of the time it will be severe drought because deficient and dry condition, severe dry condition. Similarly, Gwalior district in MP, June precipitation mean is 71 mm and median is 52. So almost 26 to 27% deficient will be there for more than 50% of the years. So therefore, this percentage of normal is not a good index for that. Then the other index, Palmer Drought Severity Index, was developed, but there is a problem. This when condition changes from dry to normal or wet, it suddenly changes from negative to positive. So that changes is very rapid in the index. So therefore, it is not that stable. And drought monitoring has started by India Meteorological Departments since 1967. Because there was a drought, a consecutive drought in 65 and 66, and Planning Commission has recommended IMD to start drought research and monitoring, and then at Pune, IMD Pune, it has started. So IMD monitors drought by using 4 well-established drought indices. One is percent of normal, that is I have discussed, then aridity anomaly index, then standardized precipitation index, and then standardized precipitation evapotranspiration index. So aridity index also calculated the ratio of water deficit to water demand, and this is also IMD is monitoring agriculture drought during both Kharif and Rabi seasons using a wide network of stations using aridity anomaly. And this is what the contingency table of 2016. So, and GFS model has been used to forecast. So, it is found that the forecast is correct for 65% of time, and if you go only one category out, then it is 89%. So outlook issued by India Meteorological Department for uh, drought using GFS model in 2017 was mostly accurate. And then there is SPI. So this was recommended by WMO to use this, and this can be used for any time step and pressure, so weekly, monthly, seasonal, and all those things. So we fit a gamma distribution function, and then it is brought to normal distribution. So then there is no ambiguity of mean and median and all those things. And SPI is different. You can calculate for different time series for weekly, monthly, seasonal, and whatnot. So the merits are minimum data requirement is there, and simple and quick. And demerit is it is only using rainfall. And these are the categories from extremely drought to extremely wet. So flood and drought both can be monitored using these indices, SPI and all indices we can. So IMD has started monitoring drought situations in district scale using SPI since January 2013 and monthly scale as a part of climate monitoring. And this is just in 2019 monitoring. So you can see that in June, almost 74 districts, which are comprising almost 8%, and were severely to extremely dry, and 122, that is 16.15%, were moderately dry. But this situation has improved drastically by the end of season, and there is only, you can say, 1% here in the severe dry conditions, 7 districts, and only 22 districts in the moderately dry conditions. So this type of monitoring helps how the situation is improving. And also SPI outlook forecast has been also given, outlook has been given based on extended range forecast in 2018. And it has shown that all the districts and this within one category out, 73.4% forecast. So these two same category, one category out. So it is almost useful for 74% of districts. So forecast is very useful, and this is 4-week forecast. So, and now the most used index instead of SPI is SPEI. So evapotranspiration and precipitation index. So this is actually the water deficiency and the effect of this evapotranspiration on drought severity. So potential evapotranspiration is nothing but the evaporation from an extended surface. So there is difference between evaporation and potential evapotranspiration. So what is the potential of that crop? So that is defined that when the short green crop is fully setting the ground and there is no dearth of water, so there is good water and it is flowing, then what will be the, so it means the PET is computed using temperature and rainfall and all those things. So not only rainfall, it also uses temperature and other things. So therefore, it is multi in character. And this is, if you see the comparison of these two, this SPI and this is SPI from 1st June to 10th September 2019, both. So there is not much difference, but still there are some regions where there is a difference you can see. So such type of difference we can get. There are various reasons. So obviously these two are different. Now the government of India in 2016 December, so from 2017 it has been, so they have revised the manual for drought management. And this, so three, there are different steps. So first step is, which is mandatory, to see rainfall deviation. So either through SPI or dry spell or whatever matrix, the matrix is given after this. So deficiency of rainfall, dry spell, yes, yes. And if so, if it is yes, then you have to see step 2. In the event that the first drought trigger is set up in step 1, the impact indicators will be examined as the matrix. Various agencies, IMD and other, are involved into this. So these are the agencies: IMD, state government, agriculture department of, and ISRO, and CWC, Central Groundwater, and also in National Informatics, this thing, and broadcasting. So these are the parameters. So this is for crop weather watch group monitoring and information management. And they say national level, this is the dry daily conditions, delay in onset, rainfall, dry spell during critical, then state, district, and field agents. Then some things are weekly, hydrological water availability in reservoirs, stream flow, and so this is weekly, and these are fortnightly, and these are seasonal. So like that, and some things are, there is no M. Okay, so these are the way how the crop weather watch monitoring the crop. Now I am coming to forecasting. So India's farmers are beating climate change with technology. This was published in BBC News. So I get, so this is one farmer. So I get better weather forecast, so I can plan when to sow seeds or spray the plants. Otherwise, I would spend a lot of money and labor on my fields, and unexpected rains would just wash everything away, while my profits have not gone up dramatically. Technology is helping me reduce my losses. So this is, the losses are reduced what using weather forecast. This is one thing. So now a monsoon mission project has been given to IIT Gandhinagar to develop this system for forecasting in short range, and they are using hydrological model and the drought indices, reservoir and etc. They are measuring. So this is precipitation, temperature, and runoff and stream flow. So this is from using CFS model. This is what using IMD model we are getting. And IITM in Sembul showed improved over the NCEP model. So we, whatever effort has been done at IITM, IMD, MOES is good. And these are the predicted thing. This is the observed lead 7, lead 15, lead 45 forecast. And this is ensemble mean forecast. So you can see that it is up to 45 days. It has very good skill. So this is the observation, and this is the skill. So what are the MOES initiatives in this floods and droughts forecasting and other things? So MOES vision document 2030 So priorities to enhance water security, these are the points. So climate change implications towards water security, impacts on declining water's quality and quantity, and advanced. So this is a advanced weather prediction system for block level forecast. Already we have started, and is skillful for 3 to 5 days. District level forecast for 2 to 3 weeks and seasons also, and develop sector specific advisories for water resource management, agriculture, health, and other things, and develop district level weather and climate service centers for better coordination with all stakeholders on disaster management, and especially for droughts and floods, and develop an advanced regional climate services framework to cater the needs of agriculture, water resources, energy, alternative energy, health, and other things on the basis of location specific and user specific knowledge of the climate variability and predictions of climate variability, and also monitored 3-day variability of regional hydrological cycle and quantitative precipitation forecast for flood warnings and hydrological information system. So this has to be developed by 2030, maybe early to that. This is our vision, and flood warning support for the major river basins of the country. So for to tackle this, MOES has taken a massive, you can say, very big mission mode program, that is monsoon mission, and first time we are funding even from scientists, not only in India and all academia, but even from USA, UK, and Japan and other places to work on Indian monsoon and develop some forecasts. So there are basic, we are concentrating on observation online, and then short range forecast, 2 to 5 days, 7 days, then extended range from 2 week to 4 week, and seasonal for 2 months to 4 months. And there is a Center for Climate Change Research in IITM Pune. So this is working on how climate is changing and how it will change and various things. And already we have invested huge amount in computing, more than 500 crores. There are 2 computers. One is Pratyush and another is Mihir at NCMRWF, and Pratyush is IITM Pune. And this how we are giving the services. So climate trend and change from our climate change center, then seasonal forecast for seasonal group. So this climate change and trend will give you long-term planning. Seasonal will give you, make you ready, and sub-seasonal 2 to 4 week forecast will get set, and then final action is taken at short range. That is further there is nowcasting also in this. So by this we are providing the stakeholders. Sorry. And this is first time assessment of climate change over the Indian region has been published, and a detailed presentation was made by Dr. Krishnan. And in this also there is a chapter on droughts and floods and other things, how it is changing and how it will change in future. And this is just one example in 2015. So we are not only giving forecast only for India, but we are also giving forecast for other neighboring South Asian country. And this is suppose Rajasthan, so above normal, below normal 45%. And this was overlaid on district map. So what is a special month-wise distribution is required for further planning, but this was very helpful actually for this planning. If seasonal forecast was given that it will be below, when there is June is very good, and when there is very bad, so and so up to 20 days the skill is very. And this is the short range forecast of, this is 3 days forecast for the recent cyclone Amphan. And you see the observed IMD track is black, and strike probability, and what is the strike probability we have forecasted. So 99% probability is here and it was there, and these are the tracks. So on short range also we have improved a lot. So in all time scales we have improved, and we are further making by 2030 the big leap. And there is a documentation of our vision document that will tell how we are planning for different scales of prediction. So once this is done, then MOES is working on the development of multi-hazard early warning system for floods and droughts. And so for that, you have to know what are the risks from each hazard, then monitoring and warning. So already monitoring is there, part of that. So we will, with the help of CWC, this will be done, and dissemination and communication and the response capabilities. So all these things, and then integrated people-centric multi-level system is this, and this we are working on. I acknowledge various scientists from IMD, IITM, IIT Gandhinagar, IIT Bombay, BHU, and QSAT, and from our team at IITM, who have contributed a lot in this presentation and work. And thank you all.
Thank you, Dr. Sahai, for delivering such a very nice, very educative talk on droughts basics, floods basics, and prediction. So, as usual, we have received overwhelming number of questions from audience. Unfortunately, due to time limitation, we cannot attend all. However, I have kept some important questions in your chat window, so kindly attend them.
Okay, so the first question is, what is the major lacuna in the flood forecasting of the nation which needs immediate attention? Please comment. Actually, India Meteorological, so how much rain will be there uh, on the surface? This is predicted, monitored, and done by India Meteorological Department. But where it will go, this is monitored by CWC. So the flood forecasting is basically responsibility of CWC. But now, and since long, we were trying to collaborate, and all the collaboration is already there, but to work jointly. So now Honorable Home Minister has made a team, and that team is working together, and some 10 river basins have been selected. And so this is a comprehensive using India Meteorological Department and ISRO and CWC, a comprehensive mechanism is being developed to monitor floods and also to forecast the floods. The second question is, what is the main reason behind recurrent flood in Bihar and Assam? So Bihar and Assam, there are 700 rivers in Bihar, and there are many rivers. So the thing is, and there is a slope. So anything happening over the whole Himalaya, it is coming just towards Assam and Bihar. So this will, this is the region, and even there is a drought condition, suppose break condition over central India. The monsoon trough will be shifted to Himalayan region, foothills of Himalaya, and there will be torrential rains. In recent days, 2 3 days, we are observing that. So this, therefore, there is a recurrent flood in Bihar and Assam and in those regions. And the third question is how we can use GIS and remote sensing in flood forecasting. So that I have already shown to you. Forecasting also we are using the data from remote sensing, but basically the monitoring and inundation map and all these things, that is being using GIS already, it is being done. And then with satellite data, fourth question is best for real-time delineation of flood map. So one example I have shown, there may be other also. But one example I have shown you from SAT1 microwave data, and there I have shown from June to July how every day the different type of inundation and flood situations are being matched. So already that effort is there, it is on. And the fifth question is, among various types of droughts, which type of drought is increasing worldwide? Any such indication? So, of course, any other type of drought will increase. The basic is hydrological drought. So that has the number is increasing, but that is leading. So since it is very widespread and this, so that is leading the towards agriculture drought, and then finally towards the hydrological. So first is the meteorological drought. So meteorological drought is increasing already, and then that is affecting because the frequency and the duration of drought is increasing. So that is also leading towards agriculture drought and then hydrological drought. And we have experienced in India also 1 year there was no water, and from rail this drinking water. And the other thing is just this is also we have I have not shown that paper, we have just submitted. So there recent years the heat waves and so summer heat is also increasing on those years when there is a drought in the monsoon season. So this is making the situation much difficult. So thank you all for patient hearing, and I thank the computer division IITM for doing all this technical arrangements, and Dr. Vinu, and this is all what you are. Thank you.
Thank you very much, Dr. Sahai sir, for answering the queries. Thank you for your valuable time with us also. Padmakar, we can go offline now. Thank you.